All right, good morning. You guys can all hear me okay? Okay, good. Just a couple of reminders that I have up on the board. WebAssign. I created a new WebAssign class, so you might see on your Canvas twice as many assignments. This one, the new one has the correct textbook. I still haven't gotten a response from WebAssign regarding my inquiry the other day. But if you look at the assignments that start with the 9th edition, okay. If you look at the assignments that start with the 9th, it'll say 9th edition, homework 1, etc. That's the assignment you want to, the assignments you want to work on. That's the new version, that's the new class. So what I need for you to do is click on this assignment so you can establish yourself on WebAssign. One possible issue you may have with the WebAssign is this. When you took Physics 205 last semester, I'm hoping that you used your MySierra username and MySierra password, because I think WebAssign is, because you're logging in to WebAssign through Canvas, it's using those two items, the username and password of Canvas, to log you in. Okay, so if you're having trouble getting into it, it's possible that you, when you went to 205, you didn't use your MySierra username and password. That's a possibility. And if your username and password are not your MySierra username and password, then what you want to do is, before you use Canvas, log into your WebAssign and change your username and password, if you can, to the one that you used at Sierra College. Okay, so Patrick, it's working fine for you. Okay, that's fine then. I was just concerned. Okay. And again, you don't have to pay for anything since you took Physics 205 here. So, I looked at, I talked to Shakel. She said she used the 9th edition of the textbook. And so I created the new class for the 9th edition of the textbook. It should match 205 book we used last semester. I think I did something silly with the first class I created, and I accidentally picked the technology update. Okay, Patrick, so you think it's the most important thing is that you had the same login as last year? Okay. All right. All right, thank you. By the way, if at any time you can't see what I wrote down on the board, please stop me. Don't hesitate to say, hey, I can't see it. One of the problems I have is when I back myself into a corner, I have to write small. Okay, so just let me know if you can't see something, and I will try to make it bigger. I will try to use this board today. Okay, so I'll erase this board so I can have more space. All right. So are we okay with WebAssign? Are there any questions with the WebAssign? Okay, silence means there's no questions. Okay, lab kits. You should be getting an email tomorrow from our division office. They will tell you when the distribution days are. I'm going to assume that the distribution days are going to be similar to what we've been this week. Okay. In fact, it's actually good that we postponed it a week, because for our class we still haven't gotten all the equipment in. We should get it by today, I think. And then we got to put together all the kits. Okay, so we actually don't have all the material for the kits yet. Okay, we will by the end of today, and we'll probably put the kits together tomorrow. And then next week they will be available for pickup on the times that you'll be given. So I don't want to make any projections as to what times are available. We'll wait until you get the email from our division office, okay? And then I'll probably send you another email just to bug you, okay? Tutoring, and I sent you an email late last night regarding tutoring. We do have tutors available. I sent you an email with the tutors who will be available to help you, and I also gave you the Zoom address for those tutoring sessions. Okay. So, but tutoring doesn't start till Friday. Just be aware, tutoring doesn't start till Friday. And these are students who had, both these students have had 210. So they should be able to help you with homework. Additionally, once we get the lab kits distributed, etc., then we will have Tyler, you remember Tyler, our instructional assistant, he will be available to help you on your lab. And so we're going to set up some times for him so that he can help you with your labs. So you have another person to help you. Okay. Make sure you read chapter 23. And make sure you work on your first web assignment. Okay. It's going to be, this web assignment is going to tell me whether or not you want to stay in this class. It's very difficult to take attendance in an online class. And so the only way for me to see that you're interested and serious in this class is for you to work on the assignment. So make sure you work on the assignment, because if I go on the web assignment, it says you never started the assignment, it tells me you're not interested in this class. And so that's when I get to the day where I have to drop the students who are no-shows, I'm going to drop you if you haven't done the web assignment. Okay. Just be aware of that. Questions or concerns? I have a weird mark on my screen. I don't know where that came from. All right, so I'm hoping that you watched 2 videos I placed on. Somebody have a question? Yeah, if you've done the old part of the web assignment, don't worry about it, because I can't. The assignment in Canvas will still be there. I'll take care. I mean, Patrick, I'll take care of the first assignment. Don't worry about it. I'm actually probably not going to erase the first version. Once I know who's using what I'll do is I'll make the assignments available only to certain people. I'll make some of the assignments unavailable. If you're not using the first edition, I'll make the assignment unavailable. If you've done problems 1 to 8, don't worry about it. Just go on to the second. In fact, if you want to, you can complete the first assignment. If the trial doesn't expire, you can complete the first assignment, and then when you do the second assignment, go to the new edition. Okay. Other questions, concerns regarding the course? Okay, so I put 2 videos on Canvas. For the 2 problems I kind of skipped. I didn't skip them, I just didn't have time. And it seemed like people were okay with me videotaping. It was, my computer's slow for some reason.
I only saw one of the problems.
You only saw one? If you go on the discussion board, I put both of them there. One of them is a YouTube video, and the other one was one I actually had time to caption. Okay, so the second video I actually wrote my own captions for it. The first one took forever. It's taking me forever to write the captions, so I just put a YouTube video. And if somebody has trouble with it, let me know. The captioning on YouTube is a little bit weird. Okay, it was actually when I was doing the captioning for the first video with the problem where I used method 1, the captioning software, it was even more bizarre than YouTube. Okay, it would pick up me making a tap on the board as I was writing. But though I was able to change those. And so you see the second video I captioned it. The first video is auto captioned. Okay, but I don't think I'm going to have time this semester because it took me forever to do the captioning. So I apologize ahead of time if you have to deal with the YouTube captioning because the rest of the videos are probably going to do YouTube captioning. I just don't have time. Okay, all right, and I apologize ahead of time. So if you go to the discussion board, you'll see the 2 videos there. I did send two emails yesterday at different times for the videos. Okay. It's the first video that's the most important one because it shows you method 1. Let me go back. Of solving these problems. So I solved this problem in the video, and one way I did it was very physical drawing free body diagram. The other method was I used the equation with the R hat in it that I talked about the other day. So if you have questions on how I solve the problem, please don't hesitate to ask me. Okay, either via email or discussion board. Yeah, by the way, regarding, so I'm seeing some questions in the chat. Whether I'm doing the YouTube captioning or I'm doing the captioning with the software Sierra College has, it just takes forever. That's the only problem. Thanks anyway. Regarding Discord, yeah, I did. You guys got me. I'm in Discord now, so I can, when I get a chance, I can come and help you guys in Discord or in the discussion board. Granted, the school prefers you using the discussion board, but I'm gonna go with whatever works for you guys. Okay. All right. So I wanted to say one more thing regarding Coulomb's law, which is important. It's a subtle thing. It's an obvious thing, but we kind of overlook at it. Coulomb's law obeys the principle of superposition, which means that when you add the force on an object, when you look at the force on an object, it's basically a linear combination of all the forces. So for example, if I have a charge here, and I want to know the force on this charge due to some other charges, okay, let's say I want to find the force on this charge due to these two. First of all, the force between these two is independent of this guy. And the force between these two is independent of this guy. The total force depends on the two. The total force depends on a linear combination, which means you add them. Okay. Here, when we add forces, we're adding vectors. That's called a linear combination. Okay. And that's the principle of superposition. And you'll see the principle of linear superposition and all kind of topics you cover in physics. It makes the math easier when things combine, obey the principle of linear superposition. Okay, it's kind of an obvious thing. I mean, you applied this last year, last semester in 205. When you add forces, you're applying the principle of linear superposition. Okay, so what I want to do now is talk about electric fields. Okay, my computer is acting very slowly. Sorry about that. Okay, I want to talk about the electric field today. Oops. I want to talk about how to calculate I want to talk about what the electric field is. I want to talk about how to calculate the electric field for 2 cases. So that's what I'm going to spend time doing today. The first 2 items you see on the screen, they're pretty easy to do, I think. It's the last item that's hard. Calculating the electric field for continuous charge distributions. And I will say this, you have done something like this already, except it's with the gravitational field. So whatever you learned or you remember from doing gravitational fields in Physics 205, the same ideas are going to be applied here. Okay. So you're going to be using some calculus, etc. Okay. So, what is an electric field? Well, it's a field. It's like a gravitational field. The electric field gives you an idea of how great a force, a test charge will experience when you place it in the vicinity of other charges or a distribution of charges. It's just like the gravitational field strength. I got to define what is a test charge. A test charge is a charge whose value is small enough that it does not really affect the electric field produced by the other charges. Okay. Now, if you remember for gravity, find my eraser. For gravity, and let's say you're standing on the Earth. Okay, picture's like a scale, okay? So, you know that the force between you and the Earth, which is called your weight, is going to be G, the mass of the Earth, your mass over R squared. That's basically your weight. And the R is the distance from here to your center of mass, which basically is the radius of the Earth, okay? Now, the gravitational field strength, I'm not writing it as a vector yet, I'm writing it as a magnitude of a vector, is the force due to gravity divided by your mass. And we're going to define the electric field in a similar manner. So what does this mean, this number? Well, this G tells me, or tells you, if I put an object near the Earth, it's going to give me an idea how big of force the object is going to experience when I put it in the vicinity of the Earth. If I put a mass here, M1, near the vicinity of the Earth, and I know the distance from here to here, the field at this point times my mass is going to tell me how big of a force I'm going to experience. Well, we do the same thing for the electric field. The electric field is defined as the force per unit charge. The unit, one of the units we'll be dealing with for the electric field is just the Newton per Coulomb. We'll see later that we can also express the electric field as a volt per meter. The electric field is a vector. It's the force on the test charge divided by the value of the test charge. Just like for the gravitational field, it's the force due to gravity divided by the mass of the test mass. Okay? Same idea. It's a vector. Okay. Now, for a point charge, the magnitude of the electric field then is pretty straightforward because remember, Coulomb's law says K times Q1, Q2 over R squared is the electric force. So the magnitude of the electric field is F over Q. Let's say Q1. Let's make Q1 a test charge. It's going to be K Q2 over R squared. So this is the magnitude of the electric field for a point charge, which means the following. Suppose I put a charge here. And at some location in space A. One of the problems, by the way, with discussing this is I define a point charge as a dot, and not define, but I represent a point charge as a dot, and I represent a point in space as a dot. And a lot of times students think there's a charge here. There's not to be a charge here. What I'm going to do is look at what the electric field here. This Q sets up a condition in space and time. It distorts space and time so that when I put a charge here, if I wanted to put a charge there, it would experience a force. And so the electric field at this point, due to that one single charge, is given by this equation. I will just write down that the magnitude of the electric field is given by this, where R is the center-to-center distance between these 2 points. Remember, this is a point in space. This is the actual location of the charge. So pretend I had a device called a meter. Let's say I had a meter that measures electric field. So I'm moving my meter to this location A, and I'm measuring its value. That value is given by this equation. If I wanted to write this as a vector, then the vector is written in this manner. The electric field is K. You notice there's no absolute value here, okay? It's K Q over R squared R hat. And R hat, again, is our unit vector. And the unit vector points from the source of the field to the point at which it's determined, which means that in this picture, my R hat goes from my source. Okay, that's not a good one. That's my R hat. It goes from the source to point A. So I have to write down an equation that represents a unit vector. Okay? So I want to say a couple of things about the unit vector because some folks have trouble with this concept. So let me just say what a unit vector is, okay, and how you would express it. This is a quick review. Basically, it's a vector of whose length is 1. Okay. So if you remember from trigonometry, you draw the unit circle. And you remember from trigonometry, you have this thing of radius 1. This is the angle theta. And one of the things you did in trigonometry was to figure out what is the coordinates of this point on the unit circle based on its length and this angle. Well, the unit vector is based on the coordinates of the points on this unit circle. So let's say this is 60 degrees. The unit vector for this point on the unit circle is going to be cosine 60 I hat plus sine 60 j hat. That's going to be the coordinates of a point on the unit circle at theta equals 60 degrees. This is used to basically represent a direction you're going. Instead of saying 60 degrees, you can express the direction this way in vector notation. Does that make sense? one of the things that we're going to be doing a lot in problems this semester is we're going to have to determine what this unit vector is. So you have to know what it means and you have to know how to determine it. Another way to look at it is a unit vector is the length of its vector divided by its magnitude. You can determine it this way too. But I like looking at it in terms of the unit circle. Okay, so if I were, let's say I were over here, and I want to know what this unit vector is. And by the way, I was going to determine by putting this guy its tail at the origin. You see this is in the third quadrant. So the coordinates here are going to be both negative. I can just write the unit vector as, let me know if you can't see this. Okay, that would be the unit vector that represents this one right here. Does that make sense? Okay, hard to tell when we're doing this on home. Okay.
I got it.
Got it? Okay, good. So that's going to be one of the things, so that's going to be one of the difficulties in doing some of these problems, getting a unit vector. And really, when we start doing the problems that involve calculus, that's where this issue is going to come in. Okay. Because for discrete point particles, it's actually easier to actually use a physical method to calculate the electric field. I'm going to show you that. I like the physical method because it gives you some intuition as to what's going on. But when we do continuous charge distributions, we really can't do that. Too complicated. So I do want to give you some physical intuition regarding the electric field. So if we have a positive charge, which way does the electric field point? Can we come up with some sort of generalization? And instead of having you memorize something, I kind of like to have you figure out where the idea comes from. So suppose I have a positive charge. Okay? Let's say it's positive. And this is the source of the electric field. Okay, that positive charge is the source of the electric field. So I want to know how the electric field is directed anywhere within the vicinity of the charge. Can I make some sort of generalization about the electric field direction due to a positive charge? Well, let's do this. Let's say I put a test charge here. Okay? And let me write down my equation for the force on a test charge. It looks like this. Let's say this is positive. Which way is this object going to want to move? It's going to experience a repulsive force, isn't it? And doesn't it want to move to the left? So the force is in this direction. Oops. Well, if force is Q times E, E is the force over Q. So if I take the force, which points to the left, and divide by a positive number, which way is the field going to point? It's going to point to the left. Because if I divide by a positive number, that ain't going to change the direction of the vector. It's just going to change the size of the vector. Okay, so what about, and this is going to be true wherever I put that point charge. You can put the point charge here, the positive point charge, and you'll see that F and E point in the same direction, and it's going to be away, pointed away from the positive charge. You can try it. Put the point charge here, try it at home, and you'll see that the force is downward, and the electric field is downward. I put the point charge here. If I put the test charge up here, you'll see that the field is upward, and the force is upward. So, if you want to start making a generalization, it looks like the electric field, due to a positive charge, is directed away from the positive charge. But I need to make sure that I can make the generalization, I need to replace this by negative charge. Well, let's test our hypothesis here. We said after the first example that the electric field, due to a positive charge, is always directed away from the charge. Let's say I put a positive charge there. What kind of force is it going to experience? Well, it's going to be attracted to this guy. So that means that the force will be this way. It's going to be to the right. Now, what about the electric field? I'm going to take a force which is directed to the right, and I'm going to divide by the test charge, which is negative. If I divide a vector by a negative number, what that does is flip the direction of the vector, and the field is that way. So the field and the force for a negative charge are in opposite direction. But look, again, that the electric field here is pointed away from the source. And again, you can come here, you can come here, you'll get the same result. So, what are the conclusions we can make? I'll write it down on this board. If the electric field points away from a positive charge. The electric field is always directed away from the positive charge. Guess what happens for the negative charge? Make this negative. Same logic here. So let's say our source of the field is negative, and this test charge is positive. This mark is going dead. They attract each other. Right? They attract each other. Now, the electric field is the force divided by the test charge. The test charge is positive. If I take a vector and divide by a positive number, yeah, the size will change, but the direction will not. And so the electric field is still in the... Sorry about that. The electric field is still in the same direction. So notice that for a negative charge, the electric field points towards the negative charge. And again, we can change again. We can make this negative. Go through the argument again and say, oh, well, This is going to be repelling this guy, so the force is this way, which is true. But then if I take that force and divide by the test charge, which is negative, I divide a vector by a negative number, and it flips the vector by 180 degrees. So the electric field is this way. And so what that means is that the electric field points away, or points towards, and using these two facts are going to allow us to actually calculate electric fields due to simple charge distributions. Okay. It can also help us to see whether our answer is right or wrong when we do a complicated problem. So this is an important thing for you to remember. Because one, it helps you do the problems where you have a simple charge distribution, and two, it helps you determine whether your answer is right or wrong when you do a complicated problem. So this gives you some intuition as to what happens. So if I have a positive point charge, and I wanted to map out the field everywhere, let's say here, the field over here points like this, the field over here points like this, the field over here points like this, the field over here points like this. By the way, the field has an interesting property. The electric field, the gravitational field, it has an important mathematical property. These fields produce a vector in space. These fields produce a vector in space. In fact, what it does is assign a different vector at every location in space over which the field is defined.
All of those vectors are going to have same magnitude or same dimension. I don't know. You know what I mean?
These can have different. Different magnitudes and different directions at different locations in space.
But it's not uniform all around the charge.
These little vectors at locations in space, well, because the further away you go, the smaller the vector is because of. Okay.
Changes.
So if I go further over here, this vector will be smaller because of the 1 over r squared. Okay. However, the direction doesn't change there, right? I can connect all these vectors together. I can draw this line. I'm getting a little bit ahead of myself. These blue lines that I'm drawing are called electric field lines. These blue lines are the lines that connect the fields, the vectors representing the field at any point. So let me say a little bit more about what a field is, or a vector field. You have a unique vector at any point in space over which the field is defined. So the electric field, when you put a charge in space, you are distorting space and time such that you will be defining a vector, a unique vector. It's got to be a unique vector. Okay? And every point in space over which that field is defined. It's different from for example, friction. Friction does not allow you to define a unique vector at every point in space. Because if I move an object to the right or left, the direction of the vector changes. Okay. But when I put a charge here, the charge here defines a unique vector here, a unique vector here, a unique vector here. It points in a particular direction, and it has a particular length. It's one of the characteristics of a vector field. And something you will learn about in Cal 3. And yes, the magnitude decreases with distance because of the 1 over r squared term. So these little black vectors get smaller and smaller as they get further away. So if I double the distance, this should be 1/4 as big as this. Okay. So these little things are just little vectors that represents the field at a location in space. There's things called vector fields and there's things called scalar fields. A scalar field, for example, is something where you just define a certain number in space. An example would be temperature. A temperature would be a scalar field, where you can define a unique temperature everywhere in space. And then you can take the derivatives of it to figure out how it's changing. Something you learn in Cal 3. Okay. And like I said before, the field really sets up a condition in space and time, and it's characterized by these vectors. It characterizes the effects of space and time produced by a point charge or produced on a charge. Is that okay? It feels weird because it's abstract. You'll see this first unit is pretty abstract. Please, if you have a question, just don't hesitate to ask, because I know this is an abstract topic. But the fields are a real thing. You will find out later that fields carry energy. You've already learned that, because the Earth's gravitational field has energy in it. The electric field is the same thing. Now, and we talked about this the other day. The electric field acts as an intermediary agent. We talked about the example last time. I talked about, what happens if Jupiter explodes? All right? The Earth is going to experience a force, a time rate of change in momentum, but it's not going to be the same as the time rate of change in momentum of Jupiter, because it takes time for the information to go from Jupiter to the Earth. Same thing with the electric forces. It takes time for the information to propagate from point A to B. And so if something happens to some charge over here, this charge over here, which is far away, there's going to be a time lag between what happens here and what happens here. So the time rate of change in momentum of this object is going to be different from the time rate of change in momentum of this object. Where does that momentum go? Well, the field carries that. And so that resolves the issue with the problem of Newton's third law. So the field idea is a very important topic. Okay, so what I want to do now is do a couple of examples. I want to talk about calculating the electric field with a charge distribution, which this one tends to be fairly straightforward, so I'll only do one example. But then the calculus one, I'm going to do several examples. Okay. Let me check something real quick. Okay. So let's look at the electric field due to a distribution of charges. Suppose I have this charge and this charge. And I want to find the electric field here. That's a location in space. Okay. Oops. So this point P is a location in space. I want to find the field there. Basically, if I had a device that measures fields and I brought it there, I want to know what it reads. So I want to illustrate how to do this, and I want to do it the physical way. So let's pretend that this is plus 1 coulomb, and this is plus or minus 2 coulombs. I'm just going to illustrate to you what I have to do, and then I'll do an example. Electric fields, just like Coulomb's law, obeys the principle of linear superposition. So the field here, due to this object, is not affected by the field due to this object, and vice versa. So what I'm going to do is, I'm going to calculate the magnitude of the field due to this object at point P. And then I will calculate the magnitude of the field here just due to this object. And then I'm going to add them up. So I will calculate E1 and I will calculate E2. Okay. However, this is a vector, and so I got to figure out the direction of the vector. Well, I know that if this is a positive charge, the electric field always points away from the positive charge towards the object, towards the point in question. So the electric field, due to Q1 here, is going to be directed this way. And if I know that angle theta, then I can take this field, multiply by the cosine of theta, and I'll get the x component. Then I can take this quantity here, the magnitude of the field due to U1, and multiply by the sine of theta, and I'll get the y component. Then I go to this object here. Field points, oh, wrong way. The field actually points this way because it's a negative charge. The electric field points towards a negative charge, so it points like this. Here's the angle theta. In fact, let me call that theta 1. Here's theta 2. Okay, just in case they're not equal. So here's theta 2, and now what I have to do is find the x and y components produced by this point charge at this point. So you can see this vector has an x component that's positive and a y component that's negative. It's a vector that's in the fourth quadrant. This pointed tail at the origin, take this vector, put its tail at the origin, you'll see that it points in the fourth quadrant. So I'm going to take the magnitude of U2 multiplied by the cosine of theta 2. That'll give me the x component of the electric field. Then take this again, multiply by this negative sine of theta 2, because the y component is negative, and then it'll give me the y component of U2. Then I add all the x components, then I add all the y components, and then I have the magnitude of the electric field.
But we don't know the charge on P, right?
There's no, remember, that's a location in space. That's the one thing that's always confusing, right? I draw a point in space the same way as I draw a point charge. And so it looks, that looks like a point charge. I don't want to know first of all, there doesn't have to be a point charge there. Second of all, if there were, it's not going to be in the equation for calculating the electric field. Does that make sense? Maybe I should draw this as a square. Okay, as opposed to the point charges. Like just point P is just a location in space for now.
So we're just calculating the energy on that space.
The electric field.
The electric field, yeah.
Yeah. So the electric field at that point. Are we okay with that? Okay.
Yeah.
So then once we know this, the sum of the x components, once we know the sum of the y components, then I have to use the Pythagorean theorem to find the magnitude, and then the inverse tangent function to find the direction. And that's it. Now, there's a second method where you can use the r hat vector. Again, it's less physical. And what I'm going to do is, I'm going to make a video that shows this method. I won't spend a lot of time on it here. But what you do is, you know that you can write the electric field this way. So what you do in method 2, you say, okay, what is my r hat vector for each one? What is r hat? It goes from the source to the point. So here's r hat. And here's r hat. I have to write down what this r hat is, and I have to write down what this r hat is. And so my total field hopefully, if you can't see that, just let me know. That's my total field. I have to put in what the actual expression is for R1 hat and R2 hat. And here I put in the actual value of the charge, whether it's positive or negative. When I do it up here, the first way, I'm just using the magnitude of the charge. Okay. And again, this is the point where you're sampling. Okay. And that's all you do if you do the second method. It's less physical, but when you start doing the problems involving calculus, we're going to do it this way. It's way too complicated to do it the other way if I have an infinite number of charges. By the way, I want to say one more thing about the electric field. The electric field allows you to say, well, let's say I have a lot of charges. Let's say I have those black dots. Let's say these black dots are some charges in space. And I want to find the electric field at this point, P. Okay. I can derive an expression for the electric field due to all these charges at this point. Then I can ask a question. Let's say I put a charge here. So let's place a charge at point P. I can say, what is the force on the charge that I put at point P due to the electric field at point P? I don't have to say, what is the force on the charge at point P due to all these charges? In other words, I can replace a large distribution of charges with the concept of the electric field. The electric field is more general than Coulomb's law. In fact, this equation is always correct. This equation is always correct. Coulomb's law is not. Remember, I told you what the limitations of Coulomb's law were. There are situations where there is an electric field in the absence of any point charges. And if you put a charge in that region where there's an electric field, it'll experience a force. Coulomb's law cannot explain that. Let me check your chat questions here. Why is the unit vector at Q2 pointing towards? Oh, this one? Remember, the unit vector is a vector we're using method 2 now. It's a vector that's directed from the source to the point. If you multiply by the negative number in the charge, it'll make a point the other way. That make sense? Okay. Yeah, so the problem is when you're doing it mathematically, you lose that physical intuition. That's why, I show it to you. We're going to use it for the calculus problem, but when you do discrete charge distributions, you're better off doing it the physical way. Because it's hidden. When you take R2 times the negative number, you'll see that the field points this way. Okay, it's kind of hidden, it's subtle. Okay. I want to do this example. Before I do this example, I want to say one more thing. With this one. I know what the field is here. These two charges produce a condition in space called an electric field at this point. If now I decide to put a charge at this point, then if I want to find the force at that point, then I take whatever value of the charge I put here, and then multiply by the electric field, I have the force. That's it. So let's do this problem. This one's actually pretty straightforward. There's only two charges. But here I'll put in numbers. I think you kind of have the idea of what we're going to do here. You stop me if you're not understanding anything. Understanding something. Okay. So 5.00 nanocoulombs. 1 nano is 10 to the minus 9. We'll put another charge here. There are 3 charges. And let me draw these lines, just the lines that connect the charges. Just for fun. I want to know the electric field at this location. Yeah, there's a charge there. Okay, fine, there's a charge there. But I'm going to find the electric field at that location. The electric field at that location is due to this charge and this charge. The electric field at this location is not due to this one. It's not creating a field at that location because that charge is there. Okay. These two produce a field there. And then when I multiply the field at this point by the 5 nanocoulomb charge, it's going to tell me what the force that this object is experiencing. So I'm going to find the field at this point the physical way. And just to make things a little less complicated, I'm going to erase my charge just so for now, because my goal here is to figure out the field at this point. So I'm going to draw a square here. I want to find the field here. And then when I'm done, I'll put the charge there. So let's pretend I have a meter, a device that's going to sense what the field is there. It's going to give me a number. I want to figure out what that number is. So this is a negative charge. And what do we say about negative charges? The field points towards a negative charge. I'm just going to call it E3 if you don't mind. And then the field points away from a positive charge. Like that. So let me calculate the magnitudes of each one. Again, I'm not going to write the units because I don't have enough space on that board. I apologize for that. And then that's 3 nanocoulombs. I'm finding the magnitude, so I do this. And the distance is 0.1 meters. Let me do E6. And yeah, I'm not being careful with stick figures in the lecture. I will in lab. So this distance that's given is 0.3 meters. So let me look up my values that I have. So E3, the magnitude of E3 is 2,700 newtons per coulomb, and the magnitude of E6, 600 newtons per coulomb. Now I'm going to find the X and Y components. This is going to be easy. All right. E3 has only one component and it points to the left. And E6 points downward. Right? I mean, that one's pretty straight. This one's pretty straightforward. So basically, I can write the total field. This one points toward the left. And the other one points downward. There's my electric field. And both components are negative, so this is a vector that points in the third quadrant. If I want to find the magnitude of the total field, I use the Pythagorean theorem. And this will give me (2770 newtons per coulomb), and then theta is going to be the inverse tangent of the y component over the x component. And really, I don't need to write down the units because they're going to cancel. So I know that this answer is going to be the third quadrant. The calculator is going to lie to me, so I got to add 180 degrees. And this will give me 257 degrees. This is 257 from the positive x-axis. You can say it's 77 degrees below the negative x-axis. You can say it's 77 degrees south of west. However you want to describe it. Just tell me how you measure your reference. Did I have my I have to say that's wrong? Yeah, you do. I'm sorry. Yes, I do. Sorry about that. Thank you. Sorry, I made a mistake. The I's, J's are wrong. So then, this is messed up too then. Sorry about that. Yeah, otherwise the angle will be close to 180. Thank you for pointing that out. Okay. So I switched the I and J for some reason. I don't know what I did. Just not thinking that. Are we okay with this? I guess it's yes. Okay. Now, if I want to find the force on the charge I place here, then I just put the charge there. And I take this field and multiply by the charge. And what do I get? I get that from my force. By the way, just as an aside, sometimes when I write on the board, my periods are hard to see. If you can't see the period, just let me know. Because then when you watch the video, those periods are going to be hard to see. Okay, so
I was seeing that.
I'm sorry?
I was having trouble seeing them.
Yeah, just let me know and I'll make them bigger. Because sometimes I just go too fast. And even when I run on the board in the classroom, I have that issue. So. Is that better?
And that's 6.00, right? And 2.7.
This one?
Yeah.
That's 600.
Okay.
Yeah, that's 600. Yeah, this one points at the end. We're okay then? Let me do a more intuitive problem. Two of them. Again, let me check my time here. Because of the way I had everything set up here, I can't see the time. Okay, I got 12 minutes. I don't have much time. I'm going to calculate, I really don't want to calculate. I want to look at the electric field at point P for that rectangular charge distribution. So I have, let me get a better marker. A positive charge. That I put a these are actual charges, and I want to look at point P. I'm not going to do the, I don't have to do the calculation explicitly. I want to say something about the field at point P. Well, I'm going to use these ideas. Now granted, this is a rectangle, so there's some symmetry, right? Because these two sides are the same, and these two sides are the same. And if I'm at the center, the distance from any of the charges to point P is exactly the same. So let me draw what the field line looks like. These are called field lines. So for the negative charges, the electric field points toward the charge. For the positive charges, the electric field points away from the charge. Because we have our equation for E. All these R's are the same, isn't that true? Okay, let me look at this. I have a question here. Based on something said, do you consider the electric field from a point charge at the exact location of point charge to be 0? Yes. Yeah, and it is kind of weird to think about it. And we might just, when we talk about the field due to us inside the sphere, we can kind of allude to that. Okay. I know that's it's a strange thing. Isn't it true that the magnitude of the field due to all the charges is the same at point P? Isn't it true that all the angles with respect to the x-axis are the same? If I resolve these fields into components, what does it say about these x components and these x components? The angles are the same, the magnitudes are the same. So what happens to the x components? These two are equal but opposite, and these two are equal but opposite. They cancel. But the y components all point straight down. So my total electric field is going to be 4 times the y component of the fields due to one of the charges. I'm done. The total field is going to be in the negative y direction. What am I doing? I'm taking advantage of symmetry. I see that there's symmetry, and I argue that the x components cancel because the angles are the same, the distances for all of them are the same. And then all the y components point straight down. So my final answer is going to be 4 times the y components due to one of the charges. That's it, I'm done. Now let's look at the other one. You have a ring of charge, and the charge is uniformly distributed around the ring. I want to find the field at point P. This one's going to be extremely easy. What does that mean? What does that mean that the charge is distributed uniformly around the ring? Well, if I break this up into equal pieces here and here, I have the same amount of charge within these 2 little pieces. Well, if I have the same charge, let's say it's positive, then this field is going to point this way, and this field is going to point this way. Guess what happens to those arrows? They cancel. And if I go all the way around the ring and repeat this process all the way around the ring, you'll see every pair is going to cancel. So guess what the field is at the center? It's 0.
Is that how they levitate things?
I'm sorry?
Is that how they levitate things inside a ring because it's like a magnet? Like levitation?
But you got to be careful. If you're talking about a magnet, let me think about that. I'm trying to think.
You have a circle of magnets, right? And you put like a rod in between. Will it float because they all cancel each other out?
Well, if it floats, what happens is the magnetic field counteracts the field, the gravitational field.
Okay.
Yeah, here you have no field at the center. Now, granted, it doesn't mean that the field is not zero here. It's just zero at this point. If you want to figure out the field at this point, that's a lot of work. I can't even do that problem in this class. I mean, you can do it as a special project, okay? Because you can set up the integral to do it, but then you need a computer to do the integration. Okay, but the field at the center is going to be is obviously zero. Off center, it's a much more difficult problem because the integral is doesn't give you an analytical answer. You can't get an analytical solution. You have to do it on a computer. Okay, so hold on, let me check the time real quick. You saw a video where the zero still when it's off center. That's when you consider a sphere. You got to be careful. We're talking about a sphere. This is just a ring of charge. It's true if you have a solid sphere, the field anywhere within the solid sphere is zero. And we'll talk about that. Okay, I got 4 minutes. I hope you guys don't mind if I go a little bit over. But I kind of want to set this up. Okay. Now I'm going to change, and I'm going to look at the field due to a continuous charge distribution. Instead of having a bunch of point particles that represent that for a charge configuration, I'm going to know, for example, what is the field due to a uniformly charged disk or an object with some arbitrary shape. Okay, we're going to do things that have a nice shape, okay? Because we can do the integral. What do you do? So let's say I have some blob here that has charge. And I want to find the field. If I have a detector, I have a detector right here at plane P. And I want to find the field here due to that blob. Okay, that amorphous object. We're not going to do amorphous object. We're going to just nice shapes. Okay. I have to break this up into small pieces. And I have to break it up into pieces that are sufficiently small that the field, the contribution of the field due to these pieces at this point is the same over each piece. So I got to make this piece small enough so that the contribution of this field, of the field into this point, is the same over the whole side. So I actually got to make it infinitesimally small. So I actually have to break this up into a dq. And so if I break it up into a dq, then the field due to this dq, I'll call dE, is going to be k dq r hat over r squared. So I need to figure out where r hat is. Remember, r hat goes from the source to the point. So I got to write an equation for r hat. And then I need the magnitude of this guy on here. So in order to do these problems, I have to figure out where my r hat is. I need to figure out an expression for dq, and then I need to figure out an expression for r hat, which is the distance from here to here. Okay. And r hat is just the vector r over the magnitude. So this is basically the magnitude of r, of the vector r. But this thing is made up of a bunch of dq's, so I have to sum over every single dq that makes up the object. Now you folks know calculus. When I have an infinite sum of infinitesimals, this sigma becomes what? It becomes an integral. Yeah, we're going to do everything with a single integral in this class. I know, I drew something that looks like you can do a double integral. We will do things using only single integrals. Okay? We will do volumes, we will do two-dimensional objects, but we're going to do the cases where we can write everything in terms of a single integral. And it's actually good to do the problems this way because it gives you more physical intuition than just setting up a triple integral and just integrating. But that's less physical. Okay. All right. So yeah, I mean, and if you've had Calc 3, and what you want to do is maybe try to do some of these problems two different ways. It's two and three-dimensional problem. And you'll see at the beginning it's hard, but then it gets easier as you go along. Okay. So to determine the electric field due to a continuous charge distribution, first you got to choose a coordinate system. You got to then write an expression for dq. Then write an expression for r hat. Sorry about that. It's sloppy in that part. Then you find an expression for r hat and then perform integration. Now, the r hat can be a pain to do, but a lot of the problems we're going to be doing, they have symmetry to them. Okay? And so, if we can argue that certain components cancel, then we don't have to write the entire expression for r hat. Because the first problem I'm going to do, and I won't do it today, r hat is very difficult to do. I'm not going to do a video for the first example. I'm going to do it in class because it's a hard example. Okay. Yeah, this blob doesn't look symmetrical, but the ones I will be doing are symmetrical. Okay. So the dq and the r hat are going to be the most difficult thing. So before I end here, let me say something about the dq's. Okay. And then I'll stop, and then I'll do the example on Monday. I don't want to do a video. I might do a video anyway, just so you can go over it. But dq might be the hardest thing. The toughest thing in these problems is understanding how to write an expression for dq. So the simplest case is a rod. Let's say I have a rod of length L, and I want to know how much charge is in that little element. Okay. Well, isn't it true that the amount of charge in that little piece is the charge density times dx. And I'm going to use the Greek letter lambda to denote that. Same thing as if I actually said, oh, let's say this is L, and this is L over 4. I want to know how much charge is in here. Well, I would take my delta Q, and I would take my charge density lambda, times L over 4. That's how much charge is in here. Now, if the charge is uniformly distributed, then this is going to be Q over L. And what I'm doing is I'm making my delta x, which is L over 4 here, become infinitesimally small. I basically have the same expression. This is the charge density. This is my element of distance. Now, for a two-dimensional object like a disk, let's do a disk and say, wait a minute. This is two-dimensional. How do you do a two-dimensional object with a single integral? Let's pretend the disk has uniform charge density. Or a charge density that only depends on radius, the distance from the center. Let's say that's the case. How can I break this up into pieces so that I have the same amount of charge, or the charge density is constant over that piece? I want to break this up into smaller pieces so that the charge density is the same over that whole piece. Well, I'll break it up into rings. Of thickness dr and radius r. I'm breaking this up into rings. If the charge density is uniform and only depends on r, the charge density is going to be the same all the way around. Okay? If I take a pair of scissors and I cut this out, and for some magical way I can make this straight, I'll get a piece like that. The thickness is dr, the length of it is the circumference of the circle. So my area that's my element of area. So my charge that's in there is my charge per unit area, and I'm going to use the Greek letter sigma for 2 dimensions, times dA. So what I'm doing is breaking it up into a bunch of rings. Just imagine you take an old tree and look at the rings on an old tree. Right? The old tree has a lot of rings, right? And so, if I took the old tree, a disk from the old tree, and I wanted to determine write an expression for the mass of that disk, I could actually add the mass of every single ring that makes up that disk. That's what I'm doing here. I want to add up the charge of every ring that makes up this disk. And so, to find Q, I will integrate this expression. Now, problem 9, I'll get to the sigma in a second. Problem 9 in the homework is an exercise where you play around with determining the Q's. I put that in on purpose. It used to be a worksheet, but I put it into the web assignment. So if you have questions on it, please don't hesitate to ask. The sigma is charge per unit, then charge per unit area. And I'm going to say one more thing and then I'll stop because I'm over. Because we got to have lab. This is for charge or volume. So you have to kind of get away from the idea that, for example, mass is density times volume, because if the density is not uniform, you have to do an integral. So for an area, Q is the integral of sigma dA. or a volume, because you probably did this in Physics 205 also, where these are masses instead of charges. So this is for 3D, that's for 2D. Yeah, so next time I'm actually, the example I'm going to do is essentially the tree ring. Okay, and then I can do the disc. So I'm going to stop here, end this, and then I'm going to start the lab at 11:10. And let me end it right here real quick, and we'll start lab soon. I'll see you in the lab.